This call is now being recorded.
Good evening, everyone. Welcome to class 6th of the Aksharamaala volunteer scheme. I'll be continuing the electricity chapter, which from where I left in the last class. So let's continue. Today we will see about Ohm's law. So before that, let me remind you what we studied in last class. We studied about potential difference. Its symbol is V and units are voltage, volt, the SI units. And we also studied the current. So symbol is I and its units are ampere. So potential difference and current. Current was the flow of charges and potential difference was the work done to move the charges from one point to another point across a conductor. So now there is a question that is there any relation between these two quantities? So for that we have a experimental setup. Consider this electric circuit. There is a battery of potential difference V. You can put a key here, plug-in key. A voltmeter, an ammeter, so this is our circuit. The voltmeter has been connected across the resistor in the parallel connection, and ammeter is in series with the resistor. So now if we plug in the key here, the circuit will be completed and the current will flow in this direction from positive terminal of the battery to the negative terminal. There will be some current through the circuit and that current will show in this ammeter, and the reading for the potential difference across this resistor, say points X and Y, will the reading for it will be shown in this voltmeter here. So let's create a table here. Voltage, current, and the ratio of these two. We are doing this experiment or activity to find out if there is any relation between the voltage and current for a given piece of resistive material. So suppose we are here applying different voltages. At first we apply voltage V1, and in second case we apply voltage V2, and similarly in third case voltage V3. Suppose this voltage is V volts, this is twice of V, this is say 3 times of V, and we measure the current for these corresponding voltages I1, I2, I3. Like suppose here V1 is applied, so V1 is equal to V. Total resistance will be some, there will be something in this, that is resistance of the conductor, which we will study soon enough. The term resistance itself, what is it, what does it mean, the electrical resistance. So for now let's just focus on the voltage and the current itself. So if we apply different voltages, there will be some current values going through the circuit, and we measure those values, this one using voltmeter and this one using ammeter. Then if we calculate the V by I ratio for these few readings, what we will see is that approximately the same value of V by I is obtained in each case. The ratio of potential to the current will be approximately same for all these three cases. This is an observation of a experiment which we are conducting. So suppose if we are trying to plot a graph between these two quantities, it is the potential difference and current through the resistor, or current through the circuit for now. So this quantity is constant. So graphically, what does it mean is that if we try to plot a graph between these two quantities, suppose for V1 there is current I1, for V2 voltage there is current I2, and similarly for V3 there is current I3. If we try to plot these points on a graph, then the curve through which all these points will pass will be a straight line. This is the graphical meaning of this, that V by I is approximately constant, or it's just a constant value. Approximately same means that V by I does not change when we change the potential difference, which leads to change in the current through the circuit. So this was the observation. Now back in 1827, a German physicist named Sir George Simon Ohm found out the relationship between these two quantities. He found out the relationship between two quantities which we have studied, the current and the potential difference. What he found or observed was that the potential difference across the ends of a given metallic wire in an electric circuit is directly proportional to the current flowing through it. There is a condition also that provided its temperature remains the same. This is called Ohm's law. Now, what does it mean? Ohm's law observed, George Simon Ohms, he observed that potential difference across the ends of a given metallic wire, suppose this one only, suppose this XY is we have attached a wire here instead of this zigzag thing, just a straight wire. Then what he observed was that the potential difference across the ends of a given metallic wire in an electric circuit is directly proportional to the current flowing through it, that is the circuit. So you observe that if he changes the potential difference and current also changes, but the change was such that the potential drop across these ends, it was proportional to the current flowing through the circuit. Mathematically, what he observed was that V is proportional to I. This alpha symbol is, or the symbol of proportionality. That is, it simply means is that proportional means if we increase current, or if current increases in a circuit, then potential will increase. The potential difference, it will also increase. Or other way around, you can say if we increase the potential difference, the current will increase. So if one will decrease, then other will also decrease. That is the meaning of direct proportionality. Or we can simply say that V by I is equal to constant, which we observed in the above experimental setup also, this one, where V by I was coming approximately constant. To remove this proportionality constant from this equation, we remove the proportionality constant, put the equal to make it an equation, and you have to put a constant here. Suppose the constant is here R. This constant is just the rate which equates these two quantities, the current and the potential. Or we can just rewrite it as V is equal to I times R. Here R is the proportionality constant, and it remains constant for a given metallic wire at a given temperature. This condition, what does it signify is that this thing which we observe, that V is equal to IR, this will only hold, that is V will be proportional to current. This condition will only hold if the temperature of the system in which these wires, batteries and other things are kept, it remains constant. There is no change in temperature of the system, you can say, or the wire. That is also the reason why after taking the readings from the ammeter and voltmeter, we just plug out the key so that current does not flow through it for a longer duration of time. And otherwise, if it flows, then it will heat up the system, the wire itself, and the other components also. So it will give deviation in our Ohm's law, and the readings might slightly deviate from the straight line. And that is what we observe experimentally also. So now this constant remains, the proportionality constant, it remains constant for a given metallic wire at a given temperature. Suppose if we change the material of a wire, we have two wires, silver wire and we have a copper wire. If we apply Ohm's law, there is one proportionality constant and there is another proportionality constant. So for silver, this value will be different. For copper, this value will be different. So this R remains constant for only a given piece of material. This proportionality constant, or the constant R, it is known as electrical resistance. Just from the name, it suggests that it resists electricity. That is what is the meaning of electrical resistance. Trying to resist electricity, or in other words, you can say trying to resist the current. And what does current means is flow of charges. So electrical resistance tries to resist the flow of charges. And why does it try to resist? Because it is a property of a conductor. to resist flow of charges through it. You can simply think it of as that the matter, it has a property that it will have some mass. Similarly, a conductor has a property that it will resist the flow of charges through it. You can remember it in this way, that it is a property. The symbol we use for electrical resistance is R most of the times, and its SI unit, it is ohm, and for this we use a symbol omega. This symbol is capital omega. Just like there are alphabets in English, like capital A, small a. So similarly, there is a capital alphabet omega in Greek. For small omega, the symbol is like this. It's like W, but this is omega. So for electrical resistance, we use this symbol, capital omega. And this is the formula according to Ohm's law for electrical resistance. Now, how will we define 1 ohm of electrical resistance? Ohm is the SI unit of electrical resistance. So definition is simple. See, V is equal to I by R. Oh, sorry. Just 1 second. V is equal to IR. This implies R is equal to, I will go to this side. It will become V by I. So now how to define 1 ohm of electrical resistance? We put both these value as 1 and 1. That is 1 volt potential and 1 ampere current. So if 1 volt of potential difference is applied across a piece of conductor, and current that will pass through it on this application of potential difference through it, and if 1 volt of potential difference is applied across a piece of conductor, and if the current that will pass through it is 1 ampere, then the this piece of conductor is said to have an electrical resistance of 1 ohm. What does it mean? Simply, if you have a piece of conductor, say a wire again, X and Y, and if I apply a potential difference of 1 volt across it, that is, we put a battery of 1 volt here, and suppose I put an ammeter here. So for 1 volt, if the current passing through this circuit, the reading comes out to be 1 ampere, then this piece of material, the wire between X and Y, it is said to have 1 ohm of electrical resistance. This is the basic definition. You can also simply say that R is equal to V by I. If I apply 2 volts of potential difference and I get 2 ampere of current through it, then also the resistance will be 1 ohm. So you can define it in more than one ways. But this is how we usually define it, by putting everything as one. Another form of Ohm's law can be written like this. From this, what we have is that I is directly proportional to 1 by R, or in other words, we say I is inversely proportional to R. What is I? I is current, and what is R? R is electrical resistance. So, what does it mean is that the inverse relation, if R increases, then I will decrease. Suppose we have here 10 and I divide it by 2. I'll have my answer as 5. Now, suppose if I increase the denominator, I divide it by say 3. Now it has increased, so the value here that comes out is 3.33. So this value has decreased. If I increase it further, like 10 by 5, then it will become 2. It has further decreased and this has increased. Similarly, if I increase the R, the quantity on this side will decrease. This is the essence of inverse relation. You can try out an example. If you double the resistance, the current will half out. This is the meaning of inverse relation. And there is another component whose definition goes like this: a component used to increase or decrease the current without changing the source voltage in an electrical circuit is called variable resistance. The one we defined earlier or we just studied is called fixed resistance, whose value does not change or we cannot change it for a given room temperature. For fixed resistance, the circuit diagram or the circuit symbol is this one, the schematic representation for a fixed resistance. For a variable resistance, the diagram is like, or circuit schematic is like this, or you can also make it like this. So what does this definition says here is that a component used to increase or decrease the current, that is to regulate the current. You can increase or decrease also, but so far we were doing so by changing the battery itself, the potential difference we applied. But now the condition is that without changing the source voltage in an electrical circuit is called a variable resistance. Suppose you have an electric circuit, there is a resistor here and potential difference of V volt. If you apply Ohm's law, you will find that current through this circuit will be V by R. Now, if I want to change the current, then either I have to change voltage or I'll change the resistance. So far we were changing the voltage. We were inputting like V1, V2, V volt, twice of V volt. So in that case, the resistor which we used was a fixed resistance. Now, the other way to change I from this formula is that we keep this V fixed and we vary this, that is the resistance. That will also regulate the current, that is, it will either increase or decrease. If R increases, then current will decrease. If R decreases, then current will increase. Such resistance is known as variable resistance. If we use a variable resistance here, then the current can be changed by changing the value of R and keeping the voltage source voltage fixed. other component is, or instrument is, the rheostat. It has three terminals. It looks like something like this. You can denote it by RH. Suppose you have V voltage applied here. There will be some current through circuit I. This rheostat, there is one movable part in it. So suppose if you move this arrow to this point, then the current goes through this path and there is a resistance for a short time, then it can directly go through the circuit. So it has low resistance, like some value of resistance. And again, for the same circuit, if I put the arrow here instead of this point now, there will be more part of the resistor inside the circuit. So it will give a different resistance to the flow of charges. Depending upon the value of this resistance, the value of current will be defined. So this is called a variable resistance. Now take this circuit again. Now we will study about this resistance, the electrical resistance. Take some components like resistance, a wire with some resistance R, and take a light bulb, say, or take a motor, the toy motor which comes inside the RC remote control cars. If we take that, they all are two terminal devices. From one side the current goes in, from the other side current comes out. Now if we plug these components here, then what will happen? The circuit will be closed and current will start to flow through the circuit and through the component itself, right? Now if we remove the first component and put the second component, remove it again, then put the third component, we'll always have current flowing through the circuit for some constant value of potential. Suppose for this we measured current I1, this for this I2 and for this I3. Now what we will observe is that for different components, the current is different. That is, it may not be necessary that I1, I2 and I3 are equal. They can be different also. Now why is it so? Why the values of current are different for different components? So the answer is as as simple as that certain components offer an easy path for the flow of electric current, while other components or while others resist the flow of current. Some components they allow the current to pass easily, and some components they won't allow it to pass easily. Depending upon how they allow the current to pass, the electric current in the circuit will be different and not same for the components. So let's look why is it so. We know that motion of electrons in an electric circuit constitutes an electric current. The motion of electrons, that is the negatively charged particles inside the electrical circuit, that is the flow of charges, is the electric current. That is the basic definition of current itself. The electrons, they flow from negative terminal of battery to the positive terminal, which will constitute a current. These electrons, which constitute the current, are not completely free to move. Within a conductor. Why is it so? It's simple that the electrons, they are constrained to their atoms. Like we studied in earlier classes, the structure of atom also, that electrons are orbiting around the nucleus. So nucleus is positively charged. It keeps in force of attraction between itself and the revolving electrons. So electron cannot freely move. It has to follow some certain orbits. So electrons are constrained inside the electric circuit also, because electric circuit is made out of wires and components, and those are also made out of some material and consequently some atoms. This retardation or constraint in the motion of electrons is basically the resistance itself. That is the resistance being provided to the electrons to move. Resistance means something that opposes something. Motion of electrons through a conductor is retarded by its resistance. It's a very simple statement. Retarded means opposed by the electrical resistance. Electrical resistance means it resists the electricity. It is the current or the flow of charges. So the answer is simple for this question, that certain components allow an easy path for the flow of electric and some resist the flow. Why is it so? Because the electrons, they are not free to move. Why they are not free to move is because there are atoms in which there are nuclei which keep on attracting the nucleus, and for different material the atoms are different, so constraint for electrons are different in different materials. Hence, for different components made out of different materials, the current will not be same through the circuit. Now, or in simple sense, you can say that the resistance for different components is different. Now, let's see how this resistance varies over different materials. A conductor having some, by the word conductor itself, it indicates that it conducts electricity. But if we take a conductor which have some appreciable amount of resistance, then it is called a resistor. A piece of conductor providing or offering some appreciable amount of resistance, that is, it's noticeable. It can change the value of current in the circuit if we insert a resistor. If we insert that material, then that material is known as a resistor. And same symbol is used for like resistor or resistance. Same thing only. Resistor is just the word and resistance is the property, you can say. a component of given size that offers low resistance is a good conductor of electricity. Low electrical resistance is a good conductor. Take the example of these three components only, in which there will be least resistance, that is where the current will be the maximum. The corresponding component will have the least resistance. Suppose I3 is greater than I2 and I1, then the resistance for the motor, for this case only, will be less than the resistance. One second, it got closed. So I was saying that if I3 is greater than I2 and I1, then the resistance for the corresponding component, that is say R3 for this motor, will be less than R2, the resistance for electric bulb, and R1, that is the resistance for this piece of wire. So such a component is known as good conductor of electricity. Let me just give another example for this. Take two identical components, just two terminals. Say this is conductor 1, C1, and this is a conductor 2. Identical means their size is same, the length, breadth, the physical dimensions, they are same. Now, suppose this is silver material and suppose this is copper. So at room temperature, the resistance for first conductor, the first identical component, will be less than the resistance for the second component. If this is the case, and which is usually the case because silver, it has less resistance for same amount as compared to the copper, same amount of the material. So R1 is less than R2. This implies that the second conductor is poor conductor. Not in general, but as compared to the first one. In general, the copper is good conductor of electricity, but as compared to the silver, because silver has less resistance, then it will be considered good conductor out of the two, and we can say copper is the poor conductor out of the two. But in general, the copper is also a good conductor, which is the material which we used for the wirings in our houses also. And if there is a piece of material which is insulator, suppose you take wood or rubber material, then this insulator of same size provides even higher resistance. So this was all about electrical resistance. Now let's have a look at factors on which the electrical resistance of a conductor depends. talking about electrical conductor. So for this, to study the factors which affect the electrical resistance of a conductor, we take some conductors. Suppose this is the conductor and two terminals X and Y. This is another conductor. This is another wire of this shape. The first one, suppose, say its length is L, and for the second one, its total length is 2L. L for this part and L for this part. And take another piece of wire which is of same length as the first wire between X and Y. The length is same, but it is thicker than first wire. Say this is wire 1, wire 2 and wire 3. Now if we take these wire components and we take this circuit here, there's a glitch in this again. We restart it. If we put these wires in this circuit here, and there's a battery or the potential difference applied across this, then a current I will follow through this circuit or flow through this circuit, and that will be read in this ammeter. How many amperes is that current? So for these three different wires, we will see how this ammeter reads out the current for same potential difference applied or the same voltage source. If we put these wires here, then what we will find is that for longer wire, that is wire 2, remember V is constant, the voltage source. It applies constant potential difference. We are not changing it. For longer wire, current comes out to be less as compared to the other wires. If we put first wire in this circuit, then we measure some current value, say I1 for first, I2 for second, and I3 for third. Then for the longer wire, that is the second wire, the I2 comes out to be less as compared to the I1, which had less length. That is, its length was shorter as compared to the second wire. Other observation is that for thicker wire, that is the wire third, the current comes out to be greater than I1. If we put this thicker wire here, then the current through the circuit will be greater than the current when it was there when the first wire was put in the circuit. That is, the thick wire for the same length gives more current in the circuit. For same material, if we take the three wires out of same material, say copper, then the current increases for a thicker wire, that is the area of cross section of that wire. If we increase the area, this area of cross section of a wire, this one, then the current through the circuit will be greater as compared to the earlier current. This one will be greater, I prime. So now let's conclude, like correlate these observations. For same length L and same cross section, cross sectional area, if material also changes, then the resistance will also change. This is another point. We are still not concluding the things. That is, different materials have different resistance. If we conclude the all the observations we made, we combine them together, then we apply Ohm's law, the simple that V is equal to IR, how current is varying for constant potential. So basically, we are trying to get the relation between current and resistance. Applying Ohm's law, we can conclude the above observations as electrical resistance of a conductor depends upon, number one, its length, that is the length of this XY wire, how long it is. It depends upon its length. We are not stating how it depends, in what manner it depends. We're just saying that it depends upon its length. That is, for longer wire, we saw that the current will be less as compared to the shorter wire. Its cross section area, its cross section area, and nature of material. That is, if we change the material itself, suppose we are using copper, then we are using silver, then three wires for each material will show different variation. That is, the electrical resistance also vary with the nature of material. So these three are the factors on which it is dependent, provided that the temperature is constant of the system. The above observation, we saw that resistance increases with length because we said that I was decreasing with the length. Here, I is decreasing with the length. If I is decreasing, I is decreasing and potential is constant, it implies that I is inversely proportional to R, or R is inversely proportional to I. So if now I decreases means L increases, so L will be directly proportional to length. And the other observation is that for thicker wire, the current is more, or you can say the resistance is less. So thicker wire, area more, current more, resistance less. So inverse relation between resistance and area of cross section. Now if we combine these two relations, we land upon R is proportional to L by A. That is, the length proportionality is direct and area proportionality is inverse. To remove the proportionality symbol, we add a proportionality constant, as we did in the case of Ohm's law also, that V is equal to IR. We have R is equal to rho La, rho times L by A. This rho, this is again a Greek symbol. It is read as RHO in English. Rho. It is a proportionality constant. Proportionality. Proportionality constant. It is here the rate at which this quantity and this quantity are related. This proportionality constant, that is the rho, it is named as electrical resistivity. Remember, R is electrical resistance, rho is electrical resistivity. Resistivity is the property of material. Electrical resistivity of a material, of the conductor, it is a characteristic property of the material used. That is, it varies with the material. If we are taking one silver material and one we are taking copper material, then they both will have different resistivity. Their resistance might be same, changing their physical looks, the physical parameters, but their resistivity will always be different for a given temperature. All these things we are discussing, the temperature is always constant. This is the basic condition required to define all these things for now. So you just remember the temperature is constant until and unless we signify that it is changing. The SI unit of this quantity called electrical resistivity, these are ohm meter. It's easy to find. How can we find it? We know R is equal to rho times L by A. So from here, rho is R times A will go to the other side up and L will go down. So the units for resistance are ohm. Area is basically length into length. Suppose for say square, so it is meter square, square meter. For length it is meter, so 1 meter cuts here, and we are left with ohm meter. So these are the units for resistivity. Now there are different classes of material depending upon this value of resistivity. Let me show you a figure or a table will be the better word. You see in this table there is resistivity mentioned for different materials. Depending upon the value of resistivity for the material, that is dependent upon the property of the material or the nature of the material, the electrical resistivity is a property with which we can distinguish the different materials into different classes. If this resistivity is low, that it has a less value, suppose, or the definition says from 10 to power 8 to 10 to power minus 6 ohm meter. If the value lies between this, then this material is good conductor of electricity. You can see here also the silver, it has the uh, highest conductivity and the least resistivity. The smallest value of resistivity is for silver at a given temperature among these materials. Also silver has the least resistivity in the usable materials, you can say all the materials in the conductors. As it increases towards 10 to power minus 6, after that there is 49 into 10 to power minus 6. It's still in the order of 10 to power minus 6, but this number has become 2 digits. So it's basically 10 to power minus 5 now. It has increased by an order of 1, 10 to power 1. So these materials are now known as alloys. which have comparable resistivity as to the conductors also. So these are good conductors of electricity. But if resistivity is high, that is from the range of 10 to power 12 to 10 to power 17 ohm meter, then such materials are termed as insulators, like glass, hard rubber, these materials. Ebonite, you can simply think of it as plastic rod, maybe plastic or glass rod only. And diamond paper, the note paper of your notebooks, these all have very high resistivity and are poor conductor of electricity. Poor conductor of electricity. What does that mean is that it offers high resistance to the flow of charges through it. So this is how we classify different materials depending upon their resistivity. So we see that for uh, rho, that is electrical resistivity, it is material dependent. So for given length and area of cross section for two components, say we have two identical wires, then L by A will be constant. So this is constant. In case this is constant, R is proportional to rho, that is resistivity. So if we have rho is material dependent, then resistance is also material dependent for identical components. Okay, so now we have a little time. The applications we can quickly discuss. Why can't I choose this? I don't know. There's some glitch again. So applications. The alloys which lie between the conductors and the insulators, these materials, the constant and these are made of more than one conductor. Manganese, nichrome. These alloys, they do not oxidize easily. That is, they do not burn. If the temperature is increased, then they will not start burning. So the resistivity for them is low, and they can uh, endure higher temperatures. So these are used for heating purposes, like in the heater rods or in the kitchen also. The heaters which we use, in that there is alloy wire which has been coiled around some insulator. These alloys are used for heating purposes. Like some commonly used electrical heating devices, those are in your house, are electric iron, which we use to iron our clothes, toasters, etc. Tungsten is a conductor, you can say good conductor of electricity, but it acts as an something which has high melting point, so it is also used for emitting purposes, that is light emitting. In the electric bulb, the filament is made out of this tungsten material because it has less resistivity, so it conducts electricity easily and has also high melting temperature. So you can heat it also with electricity, but still it will not melt and it will glow. And aluminium and copper are good conductors of electricity. They are generally used in transmission lines. The one from which electricity flows to our houses or power stations. Then in our houses also the wires we make those wires out of copper material mostly because they have good conduction of electricity or low resistivity. So that's all for today. Let's summarize quickly. We studied electrical resistance. Before that, we studied Ohm's law, that is, the voltage across electrical circuit is proportional to the current flowing through it. So it gives an proportionality constant here known as electrical resistance. We studied about it, that how it depends upon the other factor, that is length, area of cross section, and nature of material. And the formula is like this: R is equal to rho LYA. This rho is electrical resistivity. For resistance, the SI units are ohm. For resistivity, the SI units are ohm meter. This resistivity is material dependent, and it is a it's, you can say, like a property to materials. So depending upon the resistivity, we use different materials for different purposes. Like for alloys, we use them for heating purposes. The conductors, we use them for conducting electricity or transmitting it over long distances. And insulator, this can be used, say, like your rubber gloves, which electrician use while fixing the electricity damages, the component, electrical component damages in your house. They will wear they will wear rubber gloves so that they do not get shock, because rubber is poor conductor and will not conduct electricity. So this was all for today, I think. Yes. Thanks for watching.